Hi, my name is Nathan Muhlenbrook, and today I'm going to be going through question 1, part 1 on the Physics 457 practice midterm number 2. So for the first question, it's asking you to find which of these expressions satisfy the wave equation, state which ones do and do not, and then find the wave speed for those expressions that do satisfy the wave equation. So there's two main approaches to this. The first one is by recognizing that any equation that's satisfying the wave equation is going to have the general form of g of x plus minus t. So from this we can see right away that there's a little bit of a giveaway here. Our t here is squared, so that doesn't necessarily satisfy this, and we can already kind of predict that it's not going to satisfy the wave equation. But my personal preferred way of solving this is by crunching the math. So to do that, we're going to have to use the wave equation itself. So the wave equation is the Laplacian of f is equal to 1 over v squared df dt, but that's the double derivative with respect to time. So then we need to go through both sides of the equation and make sure that they're within a constant. So this here is going to be our constant, 1 over v squared. So if the left-hand side, the Laplacian, can be multiplied by a constant to get the right-hand side, the double time derivative, then we know that we're on the right track. So starting out with the Laplacian here is just our spatial derivatives. So we only have x in this equation, so we're going to go with the double derivative with respect to x of sine of 4x plus t squared. This is going to end up being negative. The negative comes from taking the double derivative of sine. Negative 16 of sine 4x plus t squared. So now we have one side, and we need to go for the other side with the double derivative with respect to time. And that's going to be equal to d squared over dt squared of sine 4x plus t squared. Here we have to use the chain rule, so I'm going to go through it one derivative at a time. So d over dt of 2t times cos of 4x plus t squared. And the next derivative is going to give us 2 times cos of 4x plus t squared. And also the other side is going to give us 2t plus 2t times sine, but we get the negative coming out, so this here is going to be negative 4x plus t squared. So we can see here that we've got a dead giveaway right away. This extra term of cos, that's what's preventing us from multiplying this by a constant to get the same thing on both sides of the wave equation. So we can then conclude that this equation here, f1, does not satisfy the wave equation. And that's the solution for part 1 of question 1. And today I'm back with part 2 of question 1 on the Physics 457 practice midterm number 2. So for this one we have function 2, and we can see that this function is a little bit more complicated. Now looking at this, the first thing that I want to do is I want to get rid of these vectors right here. So I'm going to rewrite this in terms, or after doing the dot product. So I'm going to take cos of this dot with this, but we know r to be x, y, z. So when we take the dot product here, we're just going to get x plus 2y minus 2z minus 6t. So this then gives us a starting point for our wave equation. So we're going to plug into the wave equation immediately here. So we're going to start with the Laplacian. So the Laplacian of f is going to be our spatial derivatives. But because we have x, y, and z here, we're going to have to do the derivatives for all of them. So we're going to do the double derivative with respect to x of f2 plus d squared over dy, and I forgot my squared here, f2 plus d squared f3 dz squared. I'm just going to run through this quickly. So we end up getting negative cos of x plus y minus 2z minus 6t minus 4 cos x plus 2y minus 2z minus 6t minus 4 cos, and I'm just going to write a twiddle here so that I don't have to rewrite the inside for a third time. All of this, it's going to be the same thing, so we can sum all of these to get negative 9 cos of x plus 2y minus 2z minus 6t. So that's the first part. Now we need to do the other side of the equation. So we're going to do d squared f over dt squared is equal to negative 6 squared, because we have to take out this 6 twice, times cos of x plus 2y minus 2z minus 6t. Now, I think it's pretty easy to see here that we are within a constant of the 2. So that means that we can plug in these back to our original wave equation, which, if you'll recall, is the Laplacian of f is equal to 1 over v squared df dt. This is the double derivative. So these are going to cancel out. So I'm just going to jump to writing negative 9 is equal to 1 over v squared times negative 6 squared. So we're going to divide this. We're going to get v squared is equal to 6 squared over 3 squared, which is also equal to 3 squared times 2 squared over 3 squared. These cancel out, and we're going to find that v is equal to 2. So we've just shown that this equation satisfies the wave equation, and we've solved for the velocity of that wave. So that's the solution to part 2 of question number 1, and thank you for listening. And I'm back again with part 3 of question 1 on the physics 457 practice midterm number 2. So here we're on to function number 3, and this one is 2x minus 3t to the power of 4 plus t squared. So again, we're kind of looking at something that doesn't fit our equation that we talked about before, which is g of x plus or minus vt. But that's okay. I want to plug this into the wave equation anyways. So we're going to start with the Laplacian. So we're going to go Laplacian of f3 is equal to, we've only got the x in this one, so it's going to be d squared dx, and we don't have to worry about dy or dz, of 2x minus 3t to the power of 4 plus t squared. We're immediately going to lose this term because it's not dependent on x, and we're going to get d squared dx squared times 4 times 3, that's from the exponent, times, I'm jumping ahead of myself here. So we're going to get 4 times 3 from the exponent, 2x minus 3t. This is all going to be to the power of 2 now. And when we took the double derivative here, we're getting the 2 out of here twice, so we're also going to get a 2 squared. So all of this is going to come out to 48 times 2x minus 3t squared. Now we need to do the other side again. So we're going to take the double derivative with respect to t of f3. And that's going to be equal to d squared over dt squared of 2x minus 3t all to the power of 4 plus t squared. So with this one, quite quickly we can see that this is going to come out to 2 plus this over here. So that's going to be 4 times 3 again. And then we're going to get 2 3s from this. So that's going to be times 3 times 3 times our 2x minus 3t to the power of 2. Now, I'm not even going to bother multiplying these out because we can see here that we've got this extra term. And this extra term is going to make it impossible for us to multiply this function by a constant and get something back that's equivalent to this. Therefore, we can conclude that this function does not satisfy the wave equation, and that's the solution to part 3. Right now, we're going to finish off the final part, part 4 of question 1 on the physics 457 midterm, practice midterm number 2. So here we've got f4, which is again dependent on only x and t. So we're just going to immediately plug this into our wave equation. So we're going to get Laplacian of f4 is equal to df dx squared, which is then equal to d dx of 18x minus 6, which is equal to 18. So that's a quick one, nice and easy. D squared of dt of f4. So this is the second part of our wave equation, the right-hand side. And we're going to go with d dt of 2t, which is obviously equal to 2. So it's pretty easy to see that these can be related by a constant because they're constants themselves. So let's plug it into the wave equation. We're going to get 18 is equal to 1 over v squared times 2. Now, you may not be the same as me, but when I wrote this midterm, this is where I messed up. I got a little bit too fast, and I immediately wrote down v is equal to 3. This is not correct. I missed something, so I'm going to go through all the steps right here. I'm just going to say v squared is equal to 2 over 18, which is equal to 1 over 9. And we'll find that v is equal to 1 over 3, not v is equal to 3 like I originally said. But that's question 1 for you on the practice midterm. It's fairly straightforward as long as you remember what your wave equation is and you remember that things can only be a constant multiple of each other if they have the same terms or basis for the terms. So that's question number 1, pardon, and see you for the next question.